Hi everyone, how are you? So the idea for today is reviewing the security incident that recently happened in NOMAD. We will be going from the very fundamentals of breaches, what breaches are, how they are made of, how those concepts apply to NOMAD. Then we will be reviewing the transactions, we will go to Tenderly, we will go step by step, understanding what actually happened. We will find the root cause of the vulnerability. Having done that, we will understand one of the transactions that actually drained some tokens from NOMAD. Then we will be reviewing the exact payload. We will be breaking it down step by step to understand exactly what happened. And afterwards, we will be seeing some tests that were published to understand better the vulnerability and be able to know in more depth what actually happened, right? So let's just get started. I should start saying that, well, we probably know that breaches are quite a critical piece of infrastructure today in Ethereum. We have seen multiple events, security incidents happening around breaches. So it's clear that by now we should all be paying more attention to them and we should all be understanding better how sensitive they are and what are the best practices to build them, right? They are quite new in the ecosystem, so it's to some extent it can be understood that, well, some critical vulnerabilities are happening in these pieces of software, right? It's clearly not that easy to get them right. So let's get started with what breaches actually are, right? From a high level, they are quite easy to understand. I'm not saying it's easy to build them and to get them right. I'm just saying it's the idea behind them. It's quite easy to understand. So what we should bear in mind is that bridges are just a way of connecting two domains. Could be, for instance, Ethereum with another sidechain. In the case for today, we will be seeing how Ethereum was connected via NOMAD with Moonbeam. If we go one step deeper into bridges, we will find that, well, they are usually made of at least three components. One component being smart contracts deployed on one of the domains. Another component being another set of contracts pretty similar to the first ones that are deployed on the second domain that we are connecting. And the third component, very important one, is the off-chain service. If we want to understand how messages are passed in breaches, it's quite simple as well. We have one account, 0x123, that wants to send a cross-domain message to domain B. In this cross-domain message, this account in domain A will specify some data. That action will be somehow notified, for instance, emitted in an event, and the off-chain service will be able to pick that notification up, will be able to verify that the message is indeed legitimate, is indeed intended for this breach, and once the message is verified, the off-chain service, we can call it an operator, a relayer, an agent, whatever you want, will be able to relay that message to the smart contracts deployed on the domain B of the breach, and those set of smart contracts will be able to pass that message finally to its final destination. A more technical example would be, for instance, passing some specific data that you want to pass to another domain, right? For instance, you might want to call the transfer function of a token. So in that case, 0x123 will just send a call to the smart contracts in domain A saying that it wants to execute a certain function with some data in domain B in a certain account. Once that happens, the off-chain service, the operator, layer, agents, etc., will be verifying that message, very, very critical step in this whole process. And once the message is verified, the off-chain service will just relay that message with the exact data, the exact payload that needs to be passed to the smart contracts in domain B, so that finally the account in domain B is called, right? So it could be, for example, executing a transfer of tokens. But well, NOMAD had an incident around this, right? So there was this similar process happening in NOMAD, but we saw a security incident in it. There are at least two very clear articles explaining what happened. These are the ones that I really liked and the ones in which I have based myself to make this presentation, okay? Lots of the things that I will be telling you today are not things that I invented, are things that I learned by reading these articles. And you can do that by yourself as well. So the first one is, of course, the official article published by NOMAD, in which they analyze from a very technical perspective what's the root cause of the vulnerability. The second one, the one at the bottom, is the one published by Coinbase, in which they not only do a technical analysis of the vulnerability, but they also give some additional context on the intelligence behind the attacks, how the funds were drained, what did the attackers did with those funds, and so on and so forth. So combining them both, I think you will get like a very clear understanding of what happened, in which context, and what are the next steps for the NOMAD team. I would definitely recommend reading them both. Particularly, I personally really like the Coinbase one. So how do these concepts apply to NOMAD, right? Well, in NOMAD, at least in Ethereum, and I will say that on other chains a similar architecture can be found, they essentially had at least two contracts. One is the replica contract, and the other one is the bridge router. The replica contract, you can see it as the one verifying messages, and you can even try to see the bridge router as just the one that is able to execute those verified messages. The replica contract had a function called process. We will be seeing some details about it, don't worry. But just from a high level view, it had a process function. That function would accept a message, just a raw set of bytes. It would use a Merkle tree to verify that message. Once that message is considered verified, is proven, it's legitimate for the system, that message is passed to the bridge router. And the bridge router just takes care of executing the message, for instance, distributing the assets. Reality is quite a bit more complex than that. And in reality, you will see that in the NOMAD architecture, you will find many proxies. These proxies shouldn't make the analysis more difficult, but just be aware that there are proxies involved. So in reality, you would need to call the process function via a proxy. That proxy would obviously delegate call to a replica contract, which had the embedded logic to verify the messages. Then the handle function of the bridge router would be called via another proxy, where the verified message would be passed. And finally, the assets would be distributed. For example, if you were executing a transfer of tokens. Let's see this process function a little bit in more depth. If you go to the code, don't worry too much about the details. You will see three things happening at least. One is that, well, at the beginning the process function is indeed verifying the message. It's doing some things that we will later see exactly what these things are about. Then it's marking the message as processed. And finally, it's sending the corresponding call to the handler, that would be the bridge router, so that the message is passed and executed. Having seen that, somebody posted this screenshot on the East Security Telegram channel. I think they actually shared the tweet, and the tweet had this image in it. Somebody was saying that at some point, some weird transactions, suspicious transactions were hitting the NOMAD bridge. When somebody noticed that, they shared that information, and everyone kind of started like jumping into a thing and trying to understand what was going on. There are many transactions here. Lots of them are quite similar between each other. Actually, you can see that they are all transferring out 100 WBTC tokens from the bridge. So something's going on probably. But let's just focus on one of them. This one. Right? I'm just picking one. In this transaction, we will find at least three things. Don't focus too much around all the details that you will see here. Let's just try to build a clear image of what is supposed to be going on. So at first we will find the process function being called, passing a weird message. We'll see what that message is about. Afterwards, the handle function is being called, right, internally within the call to process. And finally, WBTC tokens are being transferred out, which is quite suspicious because they are being transferred out to the caller of the process function, and nothing else seems to be happening. So the first question is, well, is this verification working? Could be the case that it's not working. And if it is actually the case that it's not working, we should understand what's the actual payload that the attacker is using to make that verification somehow fail, in the sense that the attacker can finally extract tokens. So let's start trying to answer the first question. Is this verification working? Probably not. We'll see why. Let's go to Tenderly, right? I usually use Tenderly to try to debug step by step these things, so I would definitely recommend that to you as well. It's free. They have a free plan that you can use. I'm not affiliated with Tenderly, just to say. So remember, there are proxies involved in here, so you will see fallback functions and getting implementations and delegate calls and blah, blah, blah. That shouldn't get in the middle of the analysis. This should be quite straightforward to understand. We end up seeing the call to process in here, in this transaction. I'm just looking at Tenderly at the same transaction we were seeing recently, right? This is not another transaction, this is the same. So first the process function is being called, right? And at the beginning we see that the message is being somehow decoded, right? So you have a raw set of bytes and the function needs to understand what's included in those sets of bytes. It needs to make sure that the message is actually well formatted and that it has the expected data within it, and actually that is proven in this Merkle tree that the contract is tracking in state. So first thing that happens is that the message is decoded and the function trying to understand where the actual destination encoded in the message is indeed the local domain. In the local domain in this case would be Ethereum. Then the message is hashed, and once you have that message hashed, the function uses it to read a value from state, right? From these messages mapping in state. The result of that is being used to call the acceptable root function. Let's try to make sense out of this. So you have a message, you hash it. Once you have the hash, you try to see where that message belongs in the Merkle tree. You obtain the root of that Merkle tree. And if it's an acceptable root, then the function continues to process the message because it understands that the message has been indeed proven already. It exists. It has a corresponding root. And then the function goes on and on and on, and well, it ends up executing the handle function and doing some additional things. But definitely there is something going on in this acceptable root function, and let's see what's that about. Let's see the input to that function and let's see the output to that function, and we can do that with Tenderly. So here we have the function called to acceptable root, and let's see the input. Well, the input is just a 0, strange enough, but not only that, but also we see that the output for the input 0 is true. So it's saying that given a root of 0, the function will return true. So a root of 0 is considered an acceptable root. Apparently, the attacker had a message. The attacker would hash that message. Using that hash, would somehow obtain a 0 from the Merkle tree as the Merkle root. That root of 0 would be passed to acceptable root function and it would just return true, saying that the message has been proven. So there's clearly something going on in here. And if we go to the acceptable root function, which checks that the root has been submitted and that the optimistic timeout period has expired, meaning that the root can be processed, the acceptable root function will indeed check that, well, the root has been submitted and that some time has passed since its submission. Remember, here the root is just a 0 for this call, so it won't go into, and remember it returns a true. So you could say, well, probably it's returning here, but if you actually go see this legacy status proven, it's actually a 1, so that's not the case. So it has to be that somehow this ends up being executed. So if this ends up being executed and returning a true, it means that the function didn't go through here. So it means that the root being a 0, when it was used as a key to read from this confirm at mapping that contains the timestamps, should contain the timestamps at which roots were confirmed in this contract, it returned somehow something different than 0 and lower than the current block timestamp, and this function returned true. So if we go back to slides, remember, let's recap what we saw. We have one mapping in state called confirmat. It has the confirmation times. Then we have the messages mapping, in which you provide the hash of a message and it will return ideally the root of the Merkle tree. If it doesn't, if that message is not on the Merkle tree, perhaps should return 0. Then we have the process function. I'm just deleting some parts here just to focus on what matters. You have the message being hashed. That hash is used to read from state, that whatever is read is passed to acceptable root function. And somehow that returns true, the require passes, and we move on. So if we use cast to actually read some data from a state at that point in time, we will see that, well, if you pass if you hash a random message, whatever message, and you try to use it as a key to read from the messages mapping, indeed, similarly correctly, will return the default entry for unproven messages, which is just a 0. Okay, so the default entry for an unproven message hash is 0. That seems to be working fine. And that's what we saw internally, right? So you read something from the messages, passing an arbitrary message hash, and it just returns 0. But now you have the acceptable root function reading from the confirm at mapping. And if you actually use cast, again, passing that 0 to confirm at, this couldn't, we couldn't see this internally, so this part is quite important. You will see that confirm at actually returns a 1. So for a root of 0, confirm at returns a 1. If it returns a 1, it means that acceptable root will actually return true. And we can actually confirm that just using cast again. We can pass a 0 to acceptable root and see that indeed, as we saw internally, it returns true. So where's the problem? Well, clearly the problem is here. You see that passing a 0 to confirm at, you get a 1. If you get a 1, acceptable root will return true. So why does this happen? If you go to the initialize function of the contract, you will actually see a couple of things. You will see that it has a committed root parameter, and that committed root, which is a trusted root from which to start the replica, it says here in the docs, that committed root is used to pre-approve the root in the confirm at mapping. Again, remember, this is a contract that is behind a proxy, so it needs to have an initialize function. In that initialize function, a committed root is being passed. That committed root is a trusted root from which to start the replica, right? For some reason, NOMAD needed this. So it meant that whatever the deployer would pass in this function as a committed root would be set as confirmed in the confirm at mapping just to a 1. And we saw that somehow we were getting a 1 when we were returning the confirm at. So it could be the case that the committed root of 0 is actually set in the confirm at mapping to a 1. And we can actually confirm that in the deployment transaction. When the initialize function is being called, you can see that a 0 is being passed as the committed root. So at that point in time, the 0 root was set at the confirm at mapping, was set to a 1, and from then on, like the attack vector for the vulnerability was opened up. So we understood that the verification is not working. The following question is now, okay, what's the actual payload? The actual payload we used by at least one of the attackers was this one. I know, it's not that easy, but let's try to make sense out of it. I really found super helpful the article from Coinbase to understand this payload. When I was doing my own analysis, I didn't have that much context on NOMAD and the things that they were doing, so it wasn't that easy to decode this payload myself. I kind of ran into some barriers. But once I read the article from Coinbase, that was super clear. So let's break it down, actually doing it just the same way they did. So we should take into account that the message is built in this way. You have an origin domain, a sender of the message, a nonce, don't worry too much about it, actually it isn't needed at all, we will see later. The destination domain, that is what's the domain in which the message is intended to be executed, the recipient, and the message body. So you can see already that you have like an outer message and an inner message contained in the message body. So let's start decoding this outer message. First, you will find the origin domain, then you will find the sender. This is the nonce, the destination domain, recipient, and the rest is the message body. And the message body is made of, again, a domain, that's information that's repeated. The token ID, we'll see what's that about, the type, a recipient, the amount, and some details hash. I know that for the outer domain, I'm just showing bytes in here, but wait a second, we will see what those bytes actually represent. But for now, let's just try to make sense out of this inner message, right? Which is a bridge message. Just to make it faster, here it is. So you have the domain decoded, the token ID, it's coded, the type, it says 03, we'll see what's that about, a recipient, an amount, and a details hash, which is just a hash. If you want to make sense out of this, we can actually, because these bytes actually represent something, right? They are probably identifiers, addresses, numbers. So if we transform this, we'll get this. We see that I'm at the top now. So the origin domain is beam. So this weird number actually represents beam. The sender address is the address of the NOMAD router on the origin chain, on the origin domain. That's mean the address on beam. The nonce is 5078, whatever that is. The destination domain in this case is ETH. The recipient is the address of the NOMAD router on the destination. And then for the message body, we have again the domain in which this bridge message is going to be executed, Ethereum. The token ID, that's the address of the token that it's about to be transferred, because this is a specific message type, which is a transfer type. So this 03 actually means transfer type in the context of NOMAD messages. So you have the address of the token, WBTC, you have the transfer type, then the recipient, that's the address of the attacker that executed this transaction. Then you have the amount, 100 WBTC, because it has 8 decimals, and the details hash. Actually, the details hash is similar to a nonce in that they are actually not important, not relevant at least for this specific transaction, but just because it's here, we can say that it's actually this weird hash is the hash of some data around the token that is being transferred, which is the symbol, the name, and the decimals. Other attackers could actually replace parts of this payload and still get successful transactions. That meant that some attackers actually changed this address or actually changed this amount and were able to continue executing similar attacks. So to recap, this is what's going on. An attacker is calling the replica contract, is passing this payload, is saying, hey, replica contract, here's a valid message that says that you have to send me some tokens to me. The replica contract is flawed, so it won't be able to tell that an attacker actually built that payload for malicious purposes. The transfer is being executed and the tokens are received by the attacker. We can actually see this on a test. Okay, so the same author that published the article in Coinbase, in the Coinbase blog, also published this test, which really shows the attack vector used by some of the attackers, and also luckily by some white hat hackers as well that were able to save some funds in the breach. At the beginning in this test, we see the tokens, the token address is being defined. Notice that we not only have WBTC, but also many other tokens that were being kept on the bridge that were actually taken away as well. Here it's declaring some addresses related to the NOMAD contracts. Then we have the domains in here. And essentially the test is just understanding for each one of the tokens how much balance there is on the bridge, then generating the payload for the caller account, the token address, and the amount of tokens in the bridge. Once the payload is created, it's passed to the process function, and once that happens, it continues to iterate over all of these tokens, and the test is executed. So there are two important things to highlight: the creation of the payload and the call to process, right? The creation of the payload is quite simple and just follows what we saw recently, right? So this function is essentially trying to build this set of bytes, okay? So you will see the origin domain, in this case Moonbeam, that is this weird number here, the address of the bridge router on the origin domain, that will be understood by the NOMAD bridge as the sender. Then the nonce, see, it could be a 0, as I told you. The destination domain, which is Ethereum, The address of the region Ethereum, again, this is just the body now. The token ID, which is the address of the token, the 03 because it's a transfer type, the recipient, the amount, and a 0 because the hash, the details hash, could be a 0. So you create the payload is passed to the process function, and that's the way in which this test passes. Perfect. So we saw the test, and now all there is to say is that remember that the Nomad team, at least at the moment of recording, is still willing to collect funds stolen or either stolen or saved by all accounts that took money from the bridge. So there is this bounty opened. I think that you will be compensated, but please go to the Nomad site, read the details of the bounty opened, and there is the address in which you can return either ETH or the ERC20 you want, so as to help the Nomad team recover. So please follow the bounty, go to their site, and let's try to help the team all together, right? So that's it for today. I think that we covered many things. From the very fundamentals of bridges, we understood how those concepts could be applied to Nomad. We saw from a high-level view the Nomad contracts, then little by little we went into the contracts themselves, into the process function, then we saw the transaction. Having seen the transaction, we went to Tenderly, we debugged it, we understood the root cause of the hack, and then we went to the payload, we decomposed the payload and understood exactly how it was built. Then we saw a test, and finally, again, to highlight, there is this bounty opened. Perfect. So that's it for today. Hopefully we can see each other on the next one. See you later.